Welcome to This Explainer. Today, we're taking a fresh, high-energy look at a seriously fascinating piece of invisible infrastructure. We're talking about Modbus. Now, this is the industry-standard protocol that silently runs almost everything around us, from the massive robotic arms in manufacturing factories to the intricate mission-critical systems inside global power plants. It is quite literally the hidden language of the industrial world.
So let's dive right into this. Have you ever wondered how millions of massive, incredibly complex industrial machines actually communicate without descending into total chaos? It sounds like some crazy feat of high-level engineering, right? Like you'd need an advanced computer science degree to even grasp it. But honestly, we can make this incredibly simple and accessible. We're going to use a super elegant mental model, nothing more than a simple chest of drawers analogy. Okay, so in the Modbus system, there is a strict hierarchy to keep things orderly. There is only one master dictating the whole flow of communication. Usually this is a PC or a programmable logic controller, a PLC. But for the sake of this explainer, I want you to just imagine that you are the master. You're the boss, the single controlling device on this network, standing right in the middle of the room. Now, what's really fascinating here is the connection itself. Because you, as the master, you don't have a million different individual phone lines going to a million different machines. No way. Instead, you share just one single communication line. We call this a common bus. Just picture it like a bright strip of tape running right along the floor, connecting you, the master, to absolutely every single device on the entire factory floor. But think about it, because everyone is sharing that one single line, the multiple receiving devices, which are known in this protocol as slaves, they need a reliable way to know when you are talking to them specifically. To stop total confusion on the bus, each one gets a unique address. So we simply call them slave ID 1, slave ID 2, and so on. It's a foolproof way to ensure that when a command goes down the line, only the actual intended recipient is paying attention.
And this brilliantly illustrates our analogy. Think of the entire network as a physical room. The master? Well, that's you. The shared common bus is just the physical floor you walk on to get around. And the slave devices? Imagine them as physical chests of drawers lining the walls of your room.
All right, let's zoom in on those machines for a second. Inside each of these slave devices, the actual data isn't just, floating around randomly in a big jumble. Absolutely not. It is stored in highly specific, meticulously organized memory slots known as registers. So the absolutely crucial point here is mapping our analogy just a step further. If the machine itself is the chest, then these memory registers are simply the individual drawers. It's exactly like memory addresses in a computer. Each drawer has its own specific number. Just picture bright, sticky notes slapped right on the front of the drawers, neatly numbered 1, 2, 3, or 4. Okay, let's move to our first major action and see how this all builds. What happens when the master wants to check an input? Like, say you need to monitor the temperature on the very first device on the line. Well, in Modbus, this specific action of retrieving an input is called a read command. Here is exactly how that plays out. As the master, you literally send a verbal request down that shared bus line saying, "Hey, slave ID 1, open drawer number 3 and tell me what's inside." Following our chest of drawers analogy, you essentially walk down that strip of tape on the floor, head directly to the first chest, you physically open drawer number 3, and you reach in and pull out a piece of paper. And when you pull out that paper and look at it, boom, it clearly says 75. The machine has just told you its current temperature is exactly 75 degrees. You show that information to the network, you put the piece of paper safely back into its exact spot, and you firmly close the drawer. That entire sequential process, targeting the chest, targeting the specific drawer, and retrieving the data, that is exactly what a read command is in Modbus. Pretty simple, right? But hey, communication isn't just a one-way street of gathering data. What if the master actually wants to execute an output? Say, after reading that 75-degree temperature, the master decides, wow, it's too hot, and wants to turn on a cooling fan located on the second device. For this, the master takes a brand new piece of paper that explicitly says, turn on. It then sends a targeted instruction, basically shouting down the bus to the second chest, "Hey, slave ID 2, take this on command and put it into drawer number 5. So following those exact instructions, you travel down the bus line directly to chest number 2. You completely bypass all the others because that unique ID targeted this specific one. You open up the 5th drawer, you drop your turn on paper command right inside that memory register, and you firmly close it. That brilliantly straightforward action of sending an instruction from the master to be explicitly deposited into a specific drawer of a specific slave, well, that is your write command. The machine registers that new piece of paper in its drawer, and as a direct result, the cooling fan spins up.
So let's step back for a second and summarize this whole explainer. The entire Modbus architecture really relies on just a few core concepts working in absolute perfect harmony. It's one master sending requests down a single shared bus. It relies on unique slave IDs so everyone knows exactly who is being spoken to. And ultimately, the whole shebang comes down to picking the right register drawer and either pulling data out with a read command or dropping a command in with a write command. It honestly feels incredibly basic when you picture it as household furniture, but this physical act of opening and closing doors, that is exactly how millions of complex machines universally talk to each other every single day. It's literally the mechanism maintaining order and efficiency on factory floors and in massive utility grids worldwide. Now that you can successfully visualize this formerly abstract concept, it really changes how you look at industrial operations, doesn't it? It turns a dense topic into something you can easily grasp and remember. And it kind of leaves you wondering, what other invisible networks and protocols are quietly running the world around you right now? Think about it. Thanks for joining me on this explainer. Keep learning and keep questioning the invisible infrastructure all around you.